Welcome back. In this part, I'm going to be talking about the proof of dynamical stability for rotationally symmetric solutions of inverse mean curvature flow that satisfy an additional curvature condition. When I say rotationally symmetric, I mean a surface in Rn+1, which is the rotated image of a curve on the x1, x2 plane about the x1 axis. So a priori, this is just the rotated image of a curve. But if you assume that the surface has spherical topology and that it's mean convex, you can verify just through kind of elementary arguments that the curve actually needs to be a graph. So you get for free something pretty special about the generating curve under mean convex and spherical topology assumptions. And the two important quantities that I want to highlight are the distance to the axis of rotation for a point, which I'll call U, and this ambient vector field W, which just points away from the axis of rotation. So in cylindrical coordinates, you'd call W dr and U just r. N-1 of the principal curvatures correspond to rotation. So at any like fixed point on N0, all the curvatures in the directions of rotation are all equal, and they all equal the R component of nu over U inverse, basically. So they're all encoded in a geometric quantity. And the other principal curvature, which I'll call K, is the curvature of the graph that generates N0. So altogether, mean curvature is equal to N-1P plus K. For a problem like this, the first thing that you want to do is just see what maximum principles give you. And actually, you get a maximum principle that applies not only to the solutions that satisfy the curvature condition, but just any rotationally symmetric sphere in general. It turns out that the principal curvature P of rotation satisfies a nice evolution equation. It doesn't look so nice initially, but what you find is that at critical points of P, its evolution equation looks really nice. Just at the critical points, and that means that maximum principles will tell you something really useful. So P is initially bounded away from 0 and infinity. You can verify this with just more arguments about mean convex spheres in Rn+1. And from a maximum principle, you can get that it decays on the order of e to the minus t over n-1 as time progresses. So this makes a lot of sense from the standpoint of an expanding flow. You'd expect expanding flows to make curvature smaller, and that is what happens here. Curvature of rotation does become smaller, but it also doesn't drop down to 0 in finite time. So what can we get from knowing this? Well, first off, the bound from below tells us that NT is always going to be a cylindrical graph about the x axis. And that means that in this case, we have embeddedness for free. If you have embeddedness for free, then the only thing you need, according to the last theorem that I proved, is global existence. I say only as if it's easy. It'll actually turn out to be kind of hard, but if we can prove global existence, we automatically know the round sphere is dynamically stable under these perturbations. The bound from above is telling us that the total curvature remains bounded. So an inverse mean curvature flow, well, of course, mean curvature needs to be non-negative, and it'll only be 0 at singularities, but it's also bounded above by its initial maximum times e to the minus t over n. Forgive me for not writing an h right here. And the fact that mean curvature is bounded and P is bounded tells us that the other curvature is bounded. And altogether, you get that the total curvature decays on the rate of e to the minus t over n-1. So if we were studying mean curvature flow, we would be done. In mean curvature flow, boundedness of the total curvature in L infinity norm is a sufficient condition to continue the flow further in time. So that would tell you that a solution to mean curvature flow existed forever. An inverse mean curvature flow, total curvature could blow up in finite time, or flow speed could blow up in finite time. So we need to still worry about the second. We need to show for these solutions that flow speed does not blow up in finite time. Actually, it turns out that that's the only thing we need to worry about. Due to theorems by Smokchik and Huskin and Eelmannen, we know finite time singularities only happen if mean curvature drops to 0 in finite time. So we're looking for a bound from below on mean curvature, or equivalently, an L infinity bound from above on flow speed. Now, if you want to approach this problem with maximum principles, there's an obstacle that comes along with studying closed rotationally symmetric surfaces, which is that they close up. So in general, quantities that might be well behaved near the nex of a surface will not be well behaved near the axis of rotation. For example, the slope of the generating graph might be well behaved near the nex, but it might not be, but it's obviously not well behaved near the points that intersect the axis. So you need some way of treating regions of the surface near the axis of rotation and away from the axis of rotation separately. So I define different regions of a rotationally symmetric surface NT. The regions in blue right here, I'm calling the left cap and the right cap. And in the picture, there's C naught minus and C naught plus. But you can do this for any surface NT. So call these C, T minus, CT plus, and LT. The region in between the caps we'll call the bridge. And basically, if you think of this surface as a cylindrical graph, the boundary of the caps just corresponds to the leftmost and rightmost maxima of the generating graph, respectively. And the bridge is everything in between. You can also define these in a purely geometric way that doesn't require you to parameterize them, but this is what they are. So if you just take the standard gauge for solving inverse mean curvature flow in, you can identify each of these regions with subsets of Sn via the embeddings. And that allows you to define open domains in the space-time Sn times 0t. So let C minus be the union of all left caps, C plus be the union of all right caps, and L the union of all bridges. If you take the interior of each of these unions right here, you get open domains in space-time. And what we'd like to do is apply maximum principles over each of these regions separately. So it's a very natural choice of boundary to apply maximum principles over. What you should think is that the boundary of each of these regions in space-time, roughly corresponds to the locations of the leftmost and rightmost maxima of the graph of the generating graph. And mean curvature is very well controlled there. So if you wanted to estimate flow speed by dividing the surface up this way, it would be a good way to do things, just because mean curvature would be controlled over your parabolic boundary. However, it's actually a little bit more subtle of a problem than that. There's this issue that you could have an initial surface and not. It evolves under inverse mean curvature flow. And as it's evolving under inverse mean curvature flow, new maxima and minima either disappear or reappear. So you could imagine if the surface was evolving, one maxima could sort of go away, and it gets like overtaken by a maxima to the right of that original maxima. And in that case, you'd have domains that looked highly irregular in time. right? So you can think of what I wrote as U in this picture as like maybe being what L would look like. You could have a maxima at this time that like suddenly disappears and gets replaced by like a maxima that's further to the right. So these are actually going to be more complicated domains to try to apply a maximum principle over, because we might have that mean curvature is controlled over the like solid lines in this picture, but not over the dotted lines, like the horizontal lines that are part of the boundary. So if you have a domain in space-time, let U intersect T be the cross sections of the domain U, and define the reduced parabolic boundary of U to be the union of all of these cross sections. So in the picture, that's basically just the solid lines in the boundary of U. And the complement of the reduced parabolic boundary within the parabolic boundary of U, you can just call that the non-cylindrical. So we might have that like something is really well controlled over the reduced parabolic boundary, but not over the non-cylindrical boundary. So this is a question: can maximum principles provide useful information about non-cylindrical domains? And the answer is yes, but you need to verify that these non-cylindrical domains satisfy an additional property. So in what I'm calling the non-cylindrical maximum principle, imagine that you have a function f that satisfies a nice differential inequality, and you want to control it over a space-time domain such that each point on its non-cylindrical boundary is a limit point of U intersect T less than T naught. So in other words, imagine you have a domain like U, and you know that every point that lies on the non-cylindrical boundary of U is approached from below in time by a sequence in U. So U needs to touch these dotted parts from below in time. If you have a domain that satisfies that criteria, then actually the maximum of F must occur on the reduced parabolic boundary. To summarize what I'm saying, we know that we have domains where mean curvature is really well behaved on the reduced parabolic boundary, but not the non-cylindrical boundary. So what you want to prove about like at least one of these domains is that it satisfies this additional criteria in the non-cylindrical maximum principle, and that will allow you to control mean curvature if you find something that satisfies a nice enough evolution equation. So, you know, this is kind of the analysis part where you get really in the weeds with details, but the point is you can apply maximum principles over these non-cylindrical domains, but they're only going to tell you something interesting if you know a little bit more about the shape of the domain. So through, you know, some techniques that I'm not going to mention here because, you know, it'll just drag us down too much in details. It turns out that the union of all bridges is a domain in space-time that satisfies the assumptions of the previous theorem. As in, like maximums can can disappear, but you can't have like new maxima appearing that like give you this. Okay, let me go back to the picture because it's easier to describe. Picture that like L is this domain U. L has this shape where you can't have it like jutting outward like this, but you can have it move inward like this. That's the point. You can show that through a few other arguments. And that means that since the inverse of mean curvature flow is bounded over the boundary of each cross section. If we can find some, maximum principle that works to bound the flow speed, we can bound the flow speed just over the bridges. And the key quantity we need to bound the flow speed in L is what I mentioned before, nu W. So if R is the distance to the X1 axis, dr nu is the key quantity here. Dr nu basically measures the slope of the generating graph of NT. So this quantity is exactly equal to 1 when you're at a critical point of the generating graph. And the steeper the slope of the generating graph, the closer this quantity is to 0. So if we combine evolution equations that involve nu dr and h, we can get a uniform bound on H inverse. But this will only work if nu dr is sufficiently close to 1. So like the slope of the generating graph is sufficiently small. So how do we ensure that the slope of the generating graph is small enough? Well, sorry, I'm getting screen share is in the way. It's hard to see. Well, if we use the estimate 3 on P and also other estimates that we can get on the height U, we can bound the size of nu dr below according to this ratio right here, the maximum value and the minimum value of P over N naught. And when 4 is smaller than n to the n over 2 to the n minus 1, we get a bound on the R component of nu from below by n to the minus 1/2. So it turns out that only when this quantity right here is this big, you can pick a nice function such that that nice function composed with nu dr times the flow speed satisfies a nice evolution equation. And then you can apply the non-cylindrical maximum principle to G right here, and it gives you a bound on the flow speed in over L, not n cross 0t, but a bound on the flow speed that makes it grow like linear plus exponential. So the key quantity we need over the bridge is basically the slope of the generating graph. You want that doesn't get too large, or equivalently that this quantity right here doesn't get too small. How do you ensure that it doesn't get too small? You use this curvature condition. So we know that flow speed is bounded nicely over L, and therefore that it's also bounded nicely over the boundary of L. And well, the boundary of L is equal to the boundary of each cap union together. So we know the flow speed is also controlled over the parabolic boundary of each cap. And that, in this case, we don't need to know that C plus and C minus have the non-cylindrical maximum principle assumption satisfied, which they don't. We can just use a standard maximum parabolic maximum principle to control H inverse over these domains. So for any t smaller than infinity, you can always locate a point in Rn plus 1 such that the support function taken with respect to that point is positive just over 1 cap. So in other words, if I pick x naught to be over here, and I like pick the right location for x naught, the support function over c plus of t taken with respect to this point will be positive. And same thing for the left cap. I could find a point over here on the axis of rotation such that if I took the support function with respect to that point, it would be positive just over this cap. So you have two positive support functions, which we'll call the left and right support functions. And these actually satisfy the same evolution equation as the flow speed. And what that means is that we can apply a maximum principle to either left or right support function times H inverse, and we can obtain a bound on H inverse here. So to put it more simply, basically the caps are star-shaped with respect to just like an appropriately chosen point in Rn+1. So if you know that you have a control on the flow speed over the boundary of each of those domains, you can do the same sort of maximum principle as in like Gerhardt's proof to get H bounded over the boundary, or H bounded by its boundary maximum. Okay, so I know I've said a lot, and I know this is just like PDE analysis, so it gets really in the weeds. So I'd like to just kind of review everything that I'm saying. So for a rotationally symmetric surface and knot, we know the solution stays embedded as long as it exists. And it also has bounded total curvature. So that means that the main goal here is to bound the flow speed above infinite time. Due to previous results by Husken and Eelmannen and Smockchick, we know that this is going to tell us long time existence, which will in turn tell us convergence back to a sphere. And we consider the regions intersecting the axis and containing the next separately, applying maximum principles over each of these. Why is the flow speed controlled over the neck regions? Well, you can combine the evolution equation for the flow speed with an evolution equation that depends on basically like the derivative of the generating graph. And as long as the derivative of the generating graph is small enough, this maximum principle will give you a control on H inverse. And you need the assumption in theorem B on the curvature of rotation to make this maximum principle work, basically. I think probably there's a way to make it work without that assumption, but I wasn't able to figure it out. H inverse is controlled over the caps because certain support functions chosen with respect to specific points will be positive over, over each cap. And if you apply theorem A, it tells you that NT is star-shaped by an explicit time, and that yields dynamical stability. Okay, so that's everything that I had to say there. Join me in the final part for a discussion on applications to